Every spinning component inside a massive industrial engine battles an invisible force, unbalance. Even a microscopic unevenness in weight can take a perfectly smooth rotation and turn it into a violent, destructive blur. That shaking translates directly into mechanical trauma. It shreds bearings, shaves years off a machine's operational lifespan, and bleeds massive amounts of wasted kinetic energy. To fix this, manufacturers rely on rotor balancing machines to detect and correct those weight irregularities. But when you go to equip a facility, you are forced to make a choice between two different systems. Engineers have to pick a side in a mechanical debate. To eliminate vibration, you must choose either absolute rigidity or yielding flexibility. The balancing industry is split down the middle by these two approaches, soft bearing and hard bearing balancing machines. The terms soft and hard refer to the physics of the internal support structures. The rotor is either anchored to a solid, immovable block or cradled by a dynamic, expanding spring system. This single design choice sets the parameters for the machine's speed, calibration, and even the type of floor it requires. Misunderstanding these structural differences is why plant managers often spend hundreds of thousands of dollars on equipment that doesn't fit their production line. The hard-bearing machine's defining trait is pure rigidity, which requires anchoring the equipment to a specialized, permanent concrete foundation. By locking everything down, the structural base actively fights the spinning rotor, restricting the physical amplitude of any unbalance or vibration. Looking at this chart tracking vibration amplitude against rotational speed, we can see the result of that rigidity. Because the machine suppresses the shaking, it has to spin the rotor at high speeds to generate enough force for the sensors to detect it. There's also a mechanical tax for this stiffness. Since the structure won't yield, the machine relies on crowned rollers to hold the rotor. This creates a pinpoint contact area that applies intense pressure, increasing the risk of damaging the rotor journals over time. This approach has an advantage. If you have a rotor that is wildly off balance straight off the manufacturing line, the rigid structure simply absorbs the violent shaking. You don't need any pre-balancing operations. It also bypasses the trial weight method. Without the need to self-calibrate for every single test, the operator can churn through testing cycles rapidly. The hard-bearing system trades mechanical gentleness for raw processing speed. The soft-bearing machine takes the opposite approach. Instead of fighting the physics, it embraces them through a suspended pendulum design and flexible roller supports. This structure is self-aligning. Rather than trying to pin the spinning mass in place, the machine's supports move in tandem with the vibration. On this graph tracking measurement sensitivity across rotational speed, you can see how moving with the vibration dictates the machine's range. The sensitivity jumps to 100% as soon as the rotor starts turning and stays elevated across the entire speed spectrum. This allows technicians to run the tests at slower, safer speeds. It also lets the machine use wide, flat rollers that distribute the pressure evenly, reducing friction damage caused by rigid systems. However, this flexibility requires a calibration trade-off. Soft-bearing machines use the trial weight method. This means the system has to teach itself how to measure every single new rotor through manual test weights before the actual balancing can begin. While that setup requirement slows down the workflow, operators can use a one-run calibrator to automate the routine and recover some of that time. Without the need for a concrete anchor, these machines are portable. You can move them directly to a client site and start testing immediately without paying for complex ISO recalibrations. The soft-bearing system sacrifices top-end speed for versatility, operational safety, and logistical freedom. Making the right choice requires looking at your own factory floor, rather than just the spec sheet. If you operate a high-volume manufacturing plant, turning out identical parts shift after shift, the hard-bearing machine is built for that environment. Because the rotors are uniform, technicians rarely have to swap out the heavy support pedestals, which mitigates the setup time disadvantage. In contrast, a repair or service shop might test a massive turbine fan in the morning and a tiny pump armature in the afternoon. In a low-volume, high-variety environment, the self-calibrating trial weight method makes the soft-bearing machine an adaptive multi-tool for unpredictable workflows. There is no single superior choice. The technology you need is dictated by the volume and variety metrics of your specific production line. Ask yourself, do you need portability? Handle a variety of rotor shapes? prioritize slower, safer testing speeds, and budget for a concrete foundation. When you align the physical constraints of the balancing machine with your specific production requirements, you eliminate unnecessary friction and keep your facility running smoothly.